Hello, my name is Nimrod, and today I will be presenting work I did with Professor Avishai at Tel Aviv University on the subject of hardware fingerprinting for the ARINC 429 Avionic bus. This work was achieved with the help of engineers at Astronautics. So, what is ARINC 429? ARINC 429 is a standard protocol for in-vehicle communication in civil avionics. For example, the wired communication between the autopilot system and the GPS in an airplane. It is the most commonly used standard in civil avionics. Despite this fact, it has not seen any major revisions since the 1980s. It is missing modern security features. In particular, it has no source authentication. Devices have no way of determining if a message came from a trusted source or not, leaving the ARINC vulnerable to attacks. We examined a way to secure the bus by using an anomaly detection system. The system is attached to the bus, monitors the communication, and produces alerts when it detects irregularities. Adding such a system is compliant with the ARINC protocol because it only requires adding a receiver to the bus, which is allowed. Therefore, this solution could be used to retrofit old or new systems. We based our experimental method on hardware fingerprinting, the process of identifying hardware by analyzing the electronic signal. A bit of background before I describe the method. In ARINC 429, data is transmitted in 32-bit words. The encoding is bipolar return to zero. Bipolar means that there are three voltage levels: high, representing the 1 symbol or the 1 bit, low, representing the 0 bit, and null. In a return to zero, the voltage returns to null levels between any two successive bits, even if they are equal. The standard defines transmitters as receivers as separate units called LRUs, line replaceable units. Each bus has exactly one transmitter and up to 20 receivers. Transmission is unidirectional. A separate bus is required for each direction of communication. What types of attack are we defending against? We are dealing with technician attacks. A technician attack involves a person with physical access to the bus making changes to the hardware. We identified three types of attack. 1. A rogue transmitter. In this type of attack, the attacker replaces a transmitter with an evil transmitter. The second transmitter is initially dormant. It looks and acts exactly like the original until at some point, ideally during the flight, it starts to transmit harmful messages. 2. A rogue receiver. Here the attacker replaces a receiver with their own device. Again, the rogue device should imitate the behavior of the original device. This receiver could be used to collect information that is exploited through other attack vectors, or perhaps it could take a more active role and disrupt the flight through other non-ARINC interfaces. 3. An additional receiver. Similar to a rogue receiver, but instead of replacing a receiver, the attacker attaches an additional one. You could think of a fourth variant, an additional transmitter. However, this attack is more difficult to pull off because the protocol does not permit connecting two transmitters to one bus. Therefore, this attack cannot be achieved with commercial off-the-shelf devices. When we connected the second transmitter to the bus, it broke the communication completely. We did not pursue research in this direction. All of the attacks assume a physical change has been made to the end devices. Hardware fingerprinting is incapable of detecting a pure software attack. On the other hand, hardware fingerprinting is able to detect hardware swap as soon as it occurs, even if the evil devices are behaving normally, while the airplane hasn't even taken off yet and it is easiest to handle the attack. Also note that while our original aim was to replace source authentication, which only protects against the first adversary model, hardware fingerprinting has the potential to detect changes in receiver components. Now that we know what we are dealing with, what can we do? We propose a multi-level approach. In the first phase, a pair-word anomaly detection. For each word, make a decision whether it is anomalous or a normal word. We achieve this by further segmenting a word and making decisions for each segment. The second phase improves performance by reading from the output of the first phase and then making a decision based on a sequence, a stream of words. This is an overview of the first phase, the pair-word anomaly detection. From left to right. Acquisition, sample the signal. Segmentation, divide the words to parts of a bit. For example, voltage rising from null to high, or descending from null to low, or flat at low, or flat at null. Feature extraction. For each segment, extract a set of features. Anomaly detection per segment. Based on the extracted features, a pre-trained anomaly detector predicts if the segment is normal or anomalous. Voting. Finally, take a vote. If the percentage of normal segments is less than a certain threshold, then mark the word as an anomaly. I'll describe in detail each one of the steps. The first step is to sample the signal. We sampled at about 50 times the bit rate, more than what is required to extract the bit values, because we will be examining the analog properties of the signal. Now we perform segmentation based on voltage levels. There are 10 types of segments: low, high, 4 transitions, null to low, low to null, null to high, and high to null, and 4 types of null, because the shape of the null depends on the bit before it and the bit after it. For example, if the first bit is 0 and the second is 1, then we get a pattern of low, null, high. So the null segment has this asymmetric rising shape. There are 4 segments per bit times 32 bits, that's 128, but the last segment is the space between words. Discarding this segment leaves us with 127 segments per word. For each of the segments, we extract features. We explode 4 types of feature sets. Time domain. Don't extract any features. Use the vector of voltage samples. Simple. Generic. Composed of mean, variance, skewness, and several other similar statistics. This feature set is inspired by feature sets used in other domains. We call this the generic feature set because it does not take into account the specific encoding of ARINC 429. Polynomial. Here we try to design a feature set that is aware of the protocol. We fit each segment with a polynomial and take the coefficients and the residual as features. The degree of the polynomial depends on the type of the segment. Handcrafted. This feature set is even more protocol specific. We quantify ripples we saw in the low and high segment types by taking difference between local extrema. For the transient segments, we measured the average slope and the deviation from a straight line. Whatever feature set we used in the previous step, after extraction, the feature vector is fed to an anomaly detector which outputs a prediction. We used the local outlier factor algorithm, which is a known density-based anomaly detector. There are many anomaly detection algorithms available. We picked local outlier factor because it's reported to perform well on network intrusion detection tasks and had a simple-to-use Python implementation. The detector needs to be trained before it can be used. It stores information extracted from normal segments during a training period. Then during tests, it uses an inner database to make decisions for the new inputs. Each segment type has its own local outlier factor. Finally, a word is considered an anomaly if the percentage of normal segments is below a certain threshold. This concludes the first phase of the algorithm, the per-word anomaly detection. How well did we do in tests? In order to test the method, we needed a dataset. Unfortunately for us, we did not find a dataset of ARINC 429 recordings, so we had to compose it ourselves. We recorded about 128,000 words with 6 different transmitters and 6 receivers. We used several types of devices: evaluation boards, test equipments, and astronautics proprietary devices. We simulated attacks by first training the algorithm on a transmitter-receiver pair, then swapping or adding a device, and then running the algorithm in test mode. This is a summary of the results. The graph we see here compares the performance of the different feature sets when set to detecting a rogue transmitter. The numbers were obtained from averaging over different pairs of transmitters and receivers. One statistic that is interesting to examine is the false alarm rate. That's the y-axis. Here in particular, it also represents the misdetection rate because we calibrated the voting threshold to the equal error rate when the misdetection and the false alarm rates are equal. Of course, we want the error rates to be as low as possible. We see that in this respect, the raw feature set performs slightly better than the polynomial and the generic. Because it requires about the same amount of memory, we consider it the winner here. The performance of the handcrafted feature set is a lot worse than the other options. One possible explanation is that its dimensionality, the number of features per segment, is too low. Next, we look at the results for detecting a rogue receiver. This task is much more challenging. The transmitter has more effect on the shape of the signal than the receiver. This is not surprising, as receivers are designed not to distort the transmission. What is interesting here is that the polynomial feature set now performs better than the other options. Different feature sets are good at detecting different attacks. All of our feature sets fail at detecting an additional receiver. The error rates here are close to 50%. We did not continue testing this attack in the second phase of the algorithm. To sum up the first phase of the algorithm, we had good success detecting a rogue transmitter using the raw feature set with a 0.12% false alarm rate. However, multiplying by the maximum rate of messages per second, we get about 3 alarms per second. This is essentially unusable. Detecting a rogue receiver with polynomial feature sets is possible, though with even greater error rates. We were not successful at detecting an additional receiver. The number of false alarms per second is still too high to use. Can we decrease it? We can lower the false alarm rate by using more information, a stream of words instead of a single word. The adversary model says that a stream is either normal or anomalous and does not switch states. When we start up the system, either an attacker has already replaced the hardware or they have not. We'll use this to our advantage. In the second phase of the algorithm, we added what we called a suspicion counter. This counter is initialized to 0, increases when the pair-word anomaly detector, the first phase, detects an anomalous word, and decreases whenever it detects a normal word. It cannot go lower than 0. When the counter reaches a threshold, that's when we actually sound the alarm. That's the output of the whole method. In our paper, we take a Markov chain approach to analyzing the behavior of the suspicion counter. We start on the left of the chain. Each anomaly causes us to move to the right, and each normal word causes us to move back left. If we reach the rightmost node, we raise the alarm, so the length of the Markov chain is the threshold. P is the probability of detecting a single word as an anomaly. For a normal stream, that is the false alarm probability. For an anomalous stream, P is just the prediction. P is the probability of detecting a single word as an anomaly. For a normal stream, that is the false alarm probability. For an anomalous stream, P is just the detection probability, and 1 minus P is the misdetection probability. Here are the results of the simulations. In the first simulation, we assume that the stream contains only normal words. This graph shows the probability of raising the alarm on a normal stream sometime during a 10-hour flight as a function of the suspicion threshold. The different lines you see are for different values of the false alarm probability of a single word. The overall false alarm probability is lowered by raising the threshold. The higher the single word false alarm probability, the higher we would need to set the suspicion threshold in order to minimize the overall false alarm probability. Even for a very high single word false alarm probability of 40%, we can make the stream false alarm probability near 0. Sounds ideal. But we know there's always a trade-off. What is it this time? It's not the misdetection probability. An anomalous stream will always be detected eventually. The question is, how fast? In the second simulation, we assume that the stream contains only anomalous words. This graph shows the time it takes to raise the alarm on an anomalous stream as a function of the threshold. More accurately, the time it takes for the probability of detection to exceed 99.999%. Each line is for a different single word detection probability. The higher the threshold, the longer it takes to detect the anomaly. For a threshold of 100, even for a low single-word detection probability of 60%, that's 40% misdetection probability, the time until detection is less than 2 seconds. For the same threshold, we saw in the previous slide that the false alarm probability is very low, making this value a good choice for the threshold. So, the suspicion counter method has potential. How well does it hold in the actual experiments? Here we see the percentage of word streams in our dataset that had a misdetect. The x-axis is the suspicion threshold, the blue trend is for the raw feature set, and the orange one is for the polynomial feature set. For a suspicion threshold of more than 17, we did not see any false alarm rates in our dataset. Let's see the trade-off. In both graphs, we plot the maximum time it took to detect an anomalous stream over all of our datasets. Again, the x-axis is the threshold. The top graph is for detecting a rogue transmitter with raw feature set, and the bottom graph is for detecting a rogue receiver with the polynomial feature set. For a threshold of 100, all rogue transmitters were detected in less than about 200 milliseconds, and all rogue receivers were detected in less than about 3 seconds. Remember that for a threshold of more than 17, we did not see any false alarms. So, at least for the dataset we used, we can find a threshold value that produces fast detection at low false alarm rates. To summarize the performance of the per-stream anomaly detection. On our dataset, we can detect a rogue transmitter swap using the raw feature set in under 200 milliseconds, and a rogue receiver swap using the polynomial feature set in under 3 seconds. The false alarm rate is low enough so that no false alarms were produced in our experiments. The third adversary model, a receiver addition, is not detected by our method. To conclude, we talked about security issues in ARINC 429 Avionic bus. We demonstrated a preliminary hardware fingerprinting method which potentially could be used to retrofit existing systems with security features. Our method takes on a multi-level approach, first making decisions at a sub-bit segment level, then at word level, and finally at a stream level. In our experiments, we achieved detection at both a low latency and at a low false alarm rate. Other takeaways we picked up along the way. We experimented with different feature sets and found that different feature sets are suitable for defending against different types of attack. We applied a Markov chain analysis to justify the usage of the suspicion counter. This is early academic work. There is more research to be made regarding the stability of the performance over time and the sensitivity of the method to environmental conditions such as temperature and voltage supply levels. Questions? Just kidding, this is a recording. Thank you.